Guys, this is Section 5 notes, or Gay-Lussac's law, and we're going to be dealing with temperature and pressure. So Boyle's law was pressure and volume, which was PV equals PV. If one goes up, the other goes down. Charles' law was dealing with temperature and volume, and they did the same thing. If temperature went up, volume went up. Well, this is going to be the same thing, so it's very similar to the last section that we had. So if you're looking at this picture and you want to know what's going on, I'm going to look at my temperatures. Look what my temperatures are doing. They are increasing. So as they increase, my pressure increases, which makes sense. You guys have seen this if you've ever heated or thrown an aerosol can into like a fire and you hear it explode. That's what's happening. So what this is telling me is as temp increases, pressure is also increasing. So it's just like last chapter. As one goes up, the other goes up. Same at if temperature goes down, then pressure will also go down. So same with like pressure in your tires. If it's cold out, your tire light might come on showing that there's less pressure. Which then this can all be tied into volume, and we'll see that in the next section. Okay, so Gay-Lussac's law states that I'm just going to have you guys do this nice and easy and simple and just write this here. Gay-Lussac says as your temperature increases, your pressure is going to increase. Right, so you can just draw an arrow down, copy it down again, whatever you want to do. All right, so let's look at this chart then. We keep seeing these charts. There we go. All right, so we're just trying to predict what's going to happen. So if I look at my temperature increased slightly, so my pressure is going to increase a little bit. If I look here, my pressure has decreased, so my temperature is going to decrease. Now this one's always a little tricky when it gives you T1, so if I look at my pressure decreased, which means my temperature is going to decrease, so my temp should be higher in the box. Right, so if this went from 10 to 5, it decreased, then this is going to have to be decreasing, so it's going to have to be a higher number. All right, now I do want you guys to watch this YouTube video.
Science is a blast with Generation Genius, a new teaching resource of science videos and...
Today on Sci Guys, Gay-Lussac's law.
Welcome to Sci Guys. I'm Ryan.
And I'm Adam, and today we're doing Gay-Lussac's law of ideal gases.
You're not Adam. You're a girl.
No, I'm Adam.
I'm confused.
Gay-Lussac's law states that the temperature and pressure of an ideal gas are directly proportional. This means that as the temperature increases, the pressure increases, and vice versa.
The equipment you're going to need for this episode includes a couple of candles,
A beaker or glass,
some water in a shallow dish to hold it in,
some food coloring,
and a butane lighter or matches.
Although we're not dealing with anything particularly hazardous in this episode, it's always a good idea to wear an apron or lab coat to protect from spills and splashes. As well as our younger viewers, always make sure to have adult supervision anytime you're dealing with fire. So what we're going to do first is fill our shallow dish with an inch or two of water. And then we're just going to add some food coloring to make it easier to see.
The next step in our experiment is to take your two candles, place them in the center of the water, and light them with the butane lighter. For the final step, take your beaker or large glass and place it over top of the candles. After a little while of having our beaker over our candles, you'll notice the candle's flames will get smaller and smaller until they're extinguished. If you watch closely, you'll see that the water level underneath our beaker begins to rise as the candles fade away. The water level will continue to rise for a short time after the candle has been fully extinguished. You'll notice that the water underneath the beaker is much higher than the water in the shallow dish. Let's look at this experiment a little closer. Gay-Lussac's law states that when a fixed amount or mass of an ideal gas is kept at a constant volume and in a closed system, then its temperature and pressure are directly proportional. What this means is that when a gas's temperature increases, its pressure increases, or as its temperature decreases, its pressure decreases. As we mentioned in our last episode, an ideal gas is a theoretical gas composed of a set of randomly moving, non-interacting particles. Under normal conditions, many gases such as oxygen, hydrogen, and some heavier gases like carbon dioxide will behave like an ideal gas. This means they follow the laws of gases such as Gay-Lussac's law. In our experiment, our beaker is filled with gaseous air molecules. The energy from our flames transfers to the air molecules, exciting them by raising their temperature. When the air molecules in our beaker are excited, they try and spread further apart, but because our beaker won't expand like a balloon, the volume of space our air molecules can take up is limited. As they try and expand in volume, the air molecules press harder and harder against the walls of our beaker and the water at its base. This increase in air pressure under our beaker causes the water level under it to be pushed lower than the water level outside of it. The higher the temperature or the more energy the air molecules get, the more pressure will be created under our beaker. As the candle flames burn, they use some of the oxygen contained in the beaker for combustion. The products of this reaction are carbon dioxide gas and water vapor. As more and more hot carbon dioxide gases and water vapor are produced, they fill up the top of our beaker, forcing the oxygen in our beaker that the candles need to burn lower and lower until the candles are extinguished. Once the flame is extinguished, the air molecules under our beaker begin to cool off, dropping in temperature and losing their excitement. This causes the amount of pressure our air molecules are exerting on the sides of our beaker and the water at its base to drop. As the pressure drops, the air under our beaker wants to be equal to the pressure outside of our beaker. This need for balance causes a pull on the sides of the beaker and the water at its base. Because it's much easier to pull water into our beaker than it is to collapse the sides of our beaker, the water in our shallow container is pulled into our beaker, raising the water level under the beaker, equalizing its pressure. By changing the temperature under our beaker, we can clearly see the directly proportional relationship between the temperature and pressure of an ideal gas. This relationship is known as Gay-Lussac's law.
That's it for Gay-Lussac's law of ideal gases. Thanks for watching.
If you enjoyed this episode, let us know in the comments below and subscribe for future episodes.
And be sure to like us on Facebook and follow us on Twitter.
If you have any questions related to this episode, or about science in general, let us know in the comments below or message us on Facebook and we'll try to help you out as best possible. Thanks.
Alright guys, let's go back to this. So let's look at the learning check. Oh, where have I put my marker? There we go. So we have a gas that has a pressure, so I know it's pressure because it tells me that right here, but also it's an ATM. And then I also have T, so this is my initial pressure and my initial temperature. Now remember on temperature, I have to change this to Kelvin. To change it to Kelvin, I'm going to add 273. So 18 plus 273 is 291 Kelvin. That is my T1. What is the new pressure? So I need my new pressure when the temperature is 62. Remember, I need to change this to Kelvin. So 62 plus 273 is 335 Kelvin. That is T2. All right, so now that I have this, it's the same as what we saw before. You have P1 over T1 equals P2 over T2. So it's the same as last section. So I'm going to put 2 over 291 equals, I do not know my new pressure, but I do know my new temperature increased to 335. So once I get this, I'm going to cross multiply. So 2 times 335, and then I'm going to divide by what is left over. So I'm going to divide by 291, and my new pressure is 2.3 ATM. Now this makes sense because look, my temperature increased slightly, so my pressure should increase slightly. All right, so that is that learning check. All right, the next learning check. Use the gas laws to complete with increase or decrease. So pressure blanks when volume decreases. So if volume decreases, then pressure is also going to decrease. B, when temperature decreases, volume is also going to decrease. What one does, the other does. All right, so pressure blanks when volume changes from 12 to 24. Well, my volume has increased, so my pressure is going to increase. And then D, volume Even though this is not in Kelvin, I can still see that my temperature increased, so my volume is also going to increase. All right, kind of seeing where we're at here. We're almost done. Okay. All right, so in class, I would ask you guys, there's vapor pressure, boiling point, and atmospheric pressure, and I would say, what do you think vapor pressure? Because you guys probably know what the word pressure means. Sometimes we have some trouble kind of putting our thoughts into words, but what do you think that vapor pressure means? What is vapor? What is pressure? And then I would ask you guys to write down what you think boiling point means. We've heard of boiling points. We know that water's boiling point is 100 degrees Celsius, but what does that mean? And then what do you think atmospheric pressure? You know what an atmosphere is, you know what pressure is. What do you think that means when we put those two words together? So what I would have you guys do is have you watch this YouTube video.
So as we add heat to water, the water molecules begin moving faster, and some of them spread out and form a gas.
So I'd have you watch this video, which I'm not going to play the whole thing. I don't want this video on YouTube to be that long. But once you watch this video, I want you guys to talk about what vapor pressure, boiling point, and atmospheric pressure is in that video. And I'm going to kind of talk about it right here. So if you look at this picture right here, this image, atmospheric pressure, it's showing it's the air pressing down on that water, on that liquid. Vapor pressure in the bubble equals, so when you get, when you hit boiling point is this right here. When this right here happens. When vapor pressure in my bubble right here, this bubble right here, when it reaches or equals my atmospheric pressure, that is when we get a bubble of air that pops up and we get boiling. So that is boiling point. When my pressure inside the bubble equals the atmospheric pressure. All right, so atmospheric pressure, pressure pushing down. Let's see here. This would be like my vapor pressure, and then I've got my boiling point. All right, so anyways, I do want you to watch that video, though. It will explain things a little bit more in depth on that, and it'll show you some good video or some good visuals of that too. So watch that, make sure you're watching that, and try to answer those to the best of your ability. Let me know if you need anything from me or if you have any questions, and I will see you guys later.